All right, now that we know some of the basics using Newton's laws, particularly N2, you got to practice and master these techniques. I want to show you my 5-step process. This is the process you should use in most cases when solving a physics problem. It always works, and it's always the fallback way to go. So make sure you pay attention and can do these things. N2 is the basic fundamental idea of first semester physics. In fact, on AP exams, and I've told people this in the past, if you write sum of the forces equals MA on an FRQ problem, you're probably right, it's probably pertinent, and you may earn a point on the problem. That's not a bad thing to do every once in a while. N2 is always true, and it serves as the basic framework for solving all our problems. So, step one, I want you to draw a picture. Drawing a picture serves to clarify things. It gives you a starting point to show you what to do. Oftentimes in physics, you don't know where to start. So by drawing a picture, it focuses your mind to do the right things. Picture doesn't have to be very good. You've seen the drawings I've done. They're not very good at all. But it should be good enough to see what's happening in the problem. Step two, you have to ID or identify all the forces. You need to find all the forces acting on the object. Make sure you remember how to tell if a force acts. Something must be touching the object if it exerts a force. It can be a ground, a spring, a rope, a hand, anything that touches the object in question. The only exception for that for right now is gravity. If we are on Earth or some other planet, then gravity will exert a force. You know that this force is mg, we call that the weight, and the direction is down towards the center of the planet. By IDing all the forces, I mean you should draw an arrow that represents the force in the direction that the force is acting. Step 3, you need to define a coordinate system. You need to pick a coordinate system in order to make the math as easy as possible. Your choice of coordinate systems cannot affect the physics of the situation. It doesn't matter which coordinate system you pick, we all should get the same answer at the end of the day. We can get different numbers because of the different trig involved, with plus or minus signs because of some weird trigonometry or other things, but the magnitude of the forces at the end all have to be the same regardless of the coordinate system we pick. So you need to pick a coordinate system that makes the math easy. We want to choose what's called an orthogonal coordinate system. Orthogonal means perpendicular, so our traditional XY coordinate systems work really, really well. There are other non-orthogonal coordinate systems that work, but the math becomes really messy, and that's probably not something you'll have to worry about till college. If you make X and Y, and if you have 3 dimensions Z, perpendicular to each other, the trigonometry works just fine. We try to pick a coordinate system where as many of the forces line up on either the X or Y axis. That reduces the amount of trig that we have to do. So a good choice of coordinate systems can make the math significantly easier. We also try to pick the coordinate system so that the motion of the object is along either X or Y, but not both. Again, this will make the math a whole bunch easier in the end. I usually show my coordinate system something like this. I usually have 2 arrows, one pointing in the X direction, one pointing in the Y direction. The arrows point in the positive directions, so we know what we're talking about. I usually put this somewhere near my picture so everyone will know what I'm talking about. While it's a minor step, it's a pretty important step. A good choice, again, can make things really easier. Step 3B. Sometimes you may have to do trigonometry on the forces. If you can't get all the forces to be along either the X or Y, you will have to do trigonometry. You don't always have to do this step. Sometimes problems are simple and you don't have to do that. But sometimes you do have to do that. So if necessary, this is where you would do the trigonometry. Step 4. You need to write N2 for all the coordinates. This is the heart of physics. This is what it's always true, and this is where you usually begin a problem. Again, if you don't know what to do with these things, if you follow this 5-step procedure, it will force your brain to follow in the right way. This step gives you the mathematical equations you'll need to solve. Physics is math-based, so there will be some math that you have to do in order to get the answers that we need. So you do the physics first, steps 1 through 4, and then step 5 will be the math part. If you've done step 3 and 3b correctly, then the number of terms on the left side of your N2 equations should be the same as the number of arrows that you show in your picture. We'll go through an example and you'll see what that looks like in cents. In fact, there has to be a one-to-one correspondence between arrows and terms. Each term on the left side of your equations have to have one unique arrow, and each arrow must correspond to one unique term in the equations. This is how you know you've probably done the problem right. Step 5. Solve the equations for anything that's necessary in the problem. After step 4, you're done with physics. Now it becomes a math problem. The math may be difficult, it may be tedious, but it's math now and not physics. And you all should be able to do math. You've heard me say before, it's always the math. So let's try an example. Here's a simple one. Consider a box of 12 kilograms on a frictionless surface. There is a rope on the box pulling to the right with a force of 26 newtons, and a second rope on the box pulling to the left with a force of 21 newtons. Find the weight, the normal force, and the acceleration in the horizontal direction. There's my picture. That's step 1. I've drawn a picture. It's not very good. I use PowerPoint to try and draw things, but you get the idea. It's clear enough to show what's happening. I've put in the 4 arrows representing the forces acting. I have the box sitting there, and it's on the ground. There's the normal force. There's the force to the right on the rope. That's 26 newtons. The force to the left, which is 21 newtons, and then the weight. And also the box is 12 kilograms. Step 2, I'll ID all the forces in my box. Notice that each of the arrows I drew in there has a name with it. FN, FR, W, and FL. I'll define a coordinate system. It was already there because I didn't do this presentation very well, but I'm going to have my traditional XY coordinate system, positive X going to the right, positive Y going up. You could pick different directions. You would get different numbers, maybe in the plus or minus, but we'd still get the same values at the end. Step 4. Now I need to write the N2 for each of the direction. That's the X and Y. So here's my equation for the X direction. F sub X, the sum of the forces in the X direction, is equal to FR minus FL. FR is positive because it's pointing in the positive X direction. FL has a negative sign because it's pointing in the negative X direction. The direction of the arrows in your pictures referred to your coordinate system will tell you if it's plus or minus. That always equals MA. My mass is 12 kilograms, and I'm talking about the acceleration in the X direction. So that's 12a sub X. Here's my equation for the Y direction now. I have Fn minus W equals 12a sub Y, but that equals 0. Again, I've got the Fn in the positive Y direction. I have the W in the negative Y direction. The direction of my arrows in my picture compared to my coordinate system shows me which is plus or minus. It's always equal to MA, but sometimes we can make the assumption that the acceleration is 0. Again, notice that each term on the left side of the equations corresponds to one arrow. There's an arrow for my right, there's an arrow for my left, there's an arrow for my weight, and there's an arrow for my normal force. Don't have to do any trig in this problem because all my directions are either in the X or Y direction. I'm going to do step 5 on the next slide, but now note we are done with physics. There's only math left to do. So step 5, we have to solve the equations we wrote down. First, the X direction. Here's the equation I wrote from before. FR minus FL equals 12a sub X. I'm going to put in numbers now. So I get 26 newtons minus 21 newtons equals 12a sub X. Continuing to solve, 26 minus 21 is 5. So 5 newtons is equal to 12a sub X. If I solve that, I find that my acceleration is 0.42 meters per second squared. Now I'm going to do the Y direction. Again, notice that I chose a sub Y to be 0. Why? Because normally boxes on the ground are not birds. I call them pterodactyls or gophers. They're not flying or digging into the ground. So sometimes, based on the problem, you can assume that the acceleration in a particular direction is 0. It's always MA, but then you can say, oh, the A must be 0 because it's not flying. We also know that weight is equal to m times g. So in this case, my weight is 12 kilograms times 10 meters per second squared, and that gives me 120 newtons. Here's my y equation from before, Fn minus W equals 0. So I get Fn minus 120 equals 0. That gives me my normal force to be 120 newtons. That solves the problem. My weight was 120 newtons. In this case, my normal force was 120 newtons, and my acceleration was 0.42 meters per second squared. Just be aware that weight and normal force are not always equal to each other. In this case, they were because they happen to be perpendicular to each other. All right, let's start this one again. Sorry about that, I had to cough. Now I'm going to do another example that's going to involve some trig. Similar to the problem we just did, but now f sub r is going to be at some angle above the horizon. That's going to make that 35 degrees. So here's my drawing again. It's not very good. There's my normal. There's my right force. There's my left force. There's my weight. I'm going to ID all the forces like I just did. So each arrow has a name by it. 3 of the 4 are up and down. 1 is at an angle. There's my coordinate system I'll define. It's fine. I'm going to use the idea that 3 of the 4 forces are along the x or y axis, but one of them is not. So I'm going to do trig on the f sub r. F sub r is again at the angle, so that's what I'm going to have to do. Once I put those new forces in, see how I've replaced them? Oh, now I'm going to have 5 arrows instead of 4 arrows. So my problem is slightly more difficult, but what I gained in this case is that all 5 of my arrows are now along the x or y, so the trig is gone at this point. I can ignore the 4 f sub r force like I said, that's why I put the squiggly line through it. I'm instead going to divide that up into f sub r cosine 35 and f sub r sine 35. Notice that if I add tip to tail the f sub r cosine 35 and the f sub r sine 35, I get my original f sub r. So all I'm really doing is replacing one force with 2 forces. Now I can write n2 for both the x and y direction. In the x direction, I get f sub r cosine 35 minus f sub l is equal to 12a sub x. Very similar to what we had before. The y equation is a little bit different. I now have 3 terms because I have 3 arrows in there. F sub n plus f sub r sine 35 minus w is equal to 12a sub y. But again, this thing is not flying, so it's going to be 0. There's an arrow for my f sub r cosine 35. There's an arrow for my f sub l. There's my normal. There's my f sub r sine 35. And there's my weight. I have 5 terms on the left side of the equations. I have 5 arrows, a 1-to-1 correspondence between the two. We're done with the physics now, so now we have to do the math. That's step 5. First in the x direction. There's the equation I just had on the previous slide. Put in the appropriate numbers. I get 26 cosine 35 minus 21 equals 12a sub x. 26 cosine 35 is equal to 21.3, so I get 21.3 minus 21 is equal to 12a sub x. That's 0.3 is equal to 12a sub x, or a sub x is now 0.025 meters per second squared. Do the y, similar way. Different equation. I have the 3 terms on the left side now. Putting in the number. Well, first of all, I know that the weight is 120 newtons. So I get f sub n plus 26 sine 35 minus 120 is equal to 0. 26 sine 35 is equal to 14.9. So I get fn plus 14.9 minus 120 is equal to 0. Fn minus 105.1 is equal to 0. That means my normal force is 105.1 newtons. Again, that solves the problem. My weight's 120 newtons. My normal force is 105.1 newtons. And my acceleration is 0.025 meters per second squared. Notice in this case that the normal force was not equal to the weight. A common mistake that people make, especially in physics, is that the normal force is always equal to the weight. That's not always true. The Fn depends upon the problem, particularly the forces that are acting and how you've drawn it in the picture. One more thing to consider in the problem. You could conceivably be pulling up hard enough to lift the box off the ground, and we should be able to check for that. Well, how does that change things up? If the box is no longer in contact with the ground, that means that the normal force is then zero. So the y equation becomes the important one, as it's the one that involves F sub n. In order to stay on the ground, the normal force has to be greater than zero. So then, I get F sub n has to be greater than the weight minus F sub r sine 35. I can solve this for F sub r. That's how much force I would have to pull up at the given angle to lift the box of the given mass off the ground. 0 has to be greater than the weight minus F sub r sine 35. We know the weight was 120 newtons, so 0 is going to be greater than or equal to 120 minus F sub r sine 35. That means F sub r sine 35 has to be greater than 120, or F sub r has to be greater than or equal to 209 newtons. In this example that we've just done, if I pulled up with a force at 35 degrees greater than 209 newtons, the box would be lifted off the ground. It's not a common problem, but it's one you should check to make sure you're not lifting things up. That's it. You should be able to do any N2 problem. There may be different types of forces, which we'll talk about in the future. There may be many of them. You may have to do trig on many of them, but in principle, they're all doable. This is the heart of physics. F always equals ma.